Okay, we're going to go through several examples of how to graph various exponential functions by applying transformations. So this is the first one we're going to look at. F of x is equal to 3 to the exponent x minus 1 and then plus 4. So we want to take a look at what the base is, and that determines what parent function we're going to start with. So here we're starting with the parent function, let's call it g of x. Is equal to 3 to the exponent x because the base here is 3. Okay, so we know how to graph that. For an x value of 0, the y value will be 1. For an x value of negative 1, it'll be 3 to the negative 1. For negative exponents, we take the reciprocal of the base, so we get 1/3. For an exponent of 1, so 3 to the 1 is 3. 3 squared is 9. And 3 cubed is 27. So we can't fit that point on our graph, but we can graph the exponential function with the points that we already have here. Okay, something like this. Currently, for this exponential function, we've got a horizontal asymptote at y equals 0. So we can put that in using a dotted line, okay, at y equals 0. And we should be sure to label our x-axis and our y-axis as well on this graph. Okay, so there's our parent function. Now we want to take a look at what transformations are being applied. So let's take a look at this function f of x. And remember that our transformations based on a parent function, so our parent function was g of x, our transformations based on this parent function g of x would be written as a times g of k times x minus d plus c. And these transformations are going to be applied the same way for an exponential parent function. Okay, so we want to look at what's happening in front of the function notation piece, the g of whatever, and that piece tells us our vertical stretch or compression, as well as if it's negative, tells us if there's a reflection in the x-axis. A reminder that the k value here in the exponential function, that's going to be happening with the x in the exponent piece. So any of this stuff actually in the brackets here is happening with the x in the exponent. So if there's a k value there, that tells us the horizontal stretch or compression factor, as well as possibly a reflection in the y-axis. The d value tells us what the horizontal translation is, left or right, and the c value tells us the vertical translation, up or down. So for this function, we've got 1 in front being multiplied in front of the 3 to the x. So the a value is 1, which means there's no vertical stretch or compression, and there's no reflection in the x-axis. The k value in this function f of x is also 1, because in the exponent we have 1 times x minus 1. So we do have a d value. The d value is going to be the 1 that's here, which that represents a shift to the right 1. And the c value here is plus 4, and that's going to represent a shift up 4 units. So the only transformations that we have to do for this function would be these two right here. So what we want to do is take each of the key points that's on our parent function, y equals 3 to the x, and shift them to the right 1 and up 4. Okay, so this point from the original y-intercept, the right 1 and up 4, that point is now here. Okay, this point also shifts to the right 1, up 4, up here, and this one to the right 1, up 4, is now here. This point here, be careful because the y value is 1/3, so you have to count very carefully. So to the right 1 and up 4. So here. Now, since we've shifted up 4 units, the horizontal asymptote, which was at y equals 0, is now going to be a horizontal asymptote at y equals positive 4. It also gets shifted up 4 units. So we should put that on as a dotted line along with the label of the equation of that asymptote, y equals 4. Right? And then with that asymptote drawn in, it helps us draw in the exponential curve as well. Okay? So this is the graph of f of x. We can also state domain and range for this function after we've applied the transformations. So the domain actually hasn't changed from the parent function. All x values are still possible. So in set notation, we would say that as x is an element of all real numbers. In interval notation, we would say that x goes from negative infinity to positive infinity. Okay, for the range, the original range for the parent function was y has to be greater than 0, not equal to 0 because of the asymptote there. Now that the function's been shifted up 4 units, the range is the y values have to be greater than 4. We've shifted up the 4 units. In interval notation, that would mean that we start at 4 and go to infinity, but we don't want to include the value of 4, so we use an open bracket. All right, here's the second example. For this one, we are using the parent function y equals 2 to the x. So again, I'll call the parent function g of x. Now we want to look at the transformations that are being made. So for this function, the a value is equal to 1 because there's a 1 being multiplied by the rest of the function here. So a is 1, there's no vertical stretch or compression or reflection in the x-axis. The k value here, we can see that in the exponent. The k value is negative 1/3. So that's going to indicate a reflection in the y-axis, as well as, since the k value is negative 1/3, we take the reciprocal of that to get the horizontal stretch or compression factor. So we get that there is a horizontal stretch by a factor of 3. And that's actually all the transformations that are involved here. So first we're going to graph this parent function. So we should be able to very quickly put those points on the graph. Okay, and we do have a horizontal asymptote at y equals 0 right now. So we should put that in. Okay. Now we're going to apply these transformations to each of the key points. So let's start with the y-intercept. Reflection in the y-axis actually doesn't affect that point. And a horizontal stretch by a factor of 3 also doesn't affect that point. And so that point will remain invariant. Okay. This point here, 1, 2, reflection in the y-axis, it moves over here. Horizontal stretch by a factor of 3 means the x-coordinate is multiplied by 3, so it is now here. Okay. This point that was at 2, 4, reflection in the y-axis moves it to negative 2, 4. Horizontal stretch by a factor of 3 means the x value of negative 2 is multiplied by 3 is now at negative 6. Okay. This point is at 3, 8. So reflection means we're at negative 3, 8. Horizontal stretch by a factor of 3 means we multiply the x coordinate by 3 and we get negative 9. Okay. Finally, this point at 4, 16, we reflect, get negative 4, 16, and then we multiply the x coordinate by 3 for the horizontal stretch. So we're at negative 12. Okay. Finally, this point here at negative 1, 1/2, reflect over the y-axis and stretched horizontally by a factor of 3. Now, because we didn't have a shift up or down in this case, the asymptote has remained in the same location. This is the function f of x above. Again, we can state domain and range for this, this transformed function. The domain, all real x values, okay, or in interval notation from negative infinity to positive infinity. And the range, Because the asymptote hasn't moved, we still have y is all real numbers greater than 0, just like the parent function. Okay? Or in interval notation, y goes from 0 to infinity, but not including 0. All right, the third example. So here we have the parent function is y equals 2 to the x, since 2 is the base in this function. And the transformations that we want to list. Here, this negative, that's part of the a value. That's indicating a reflection in the x-axis. Okay. Now, this exponent here, because that's all the transformations affecting the x value, we want to make sure that that's common factored. So if we common factor what's in that exponent, we get 3 times x plus 2. So the 3 will indicate a horizontal compression by a factor of 1/3. And the 2 will indicate a shift to the left 2 units. Right, the minus 3 at the end here, that's indicating a shift down 3 units. Okay, so again, let's plot our parent function on here first. Okay, and then apply the transformations. So let's start with the y-intercept again. So reflection in the x-axis means that we're now at a y value of -1. Horizontal compression will not affect this point. And we're going to go to the left 2 units and down 3 units right here. Okay. This point here was at 1, 2. Reflection in the x-axis, the y value is at -2. Horizontal compression by 1/3 means we take the x value and multiply by 1/3. So now at 1/3, left 2 units, 1, 2, and down 3, 2, 3. That point is now here. Okay. Next point, again, reflection in the x-axis. So that means we're now at a y value of -4. Okay. Horizontal compression by 1/3, we take the x value of 2 and multiply by 1/3. So that's 2/3. Then left 2 units and down 3. Okay. Next point, 3/8. So reflection in the x-axis means we're at a y value of -8. Horizontal compression by 1/3. So 3 times 1/3 is 1. Okay, now left 2 units and down 3. Okay, next point was at 4/16, reflection in the x-axis. The y value is at -16. Horizontal compression by 1/3. 4 times 1/3 is 4/3, or 1 1/3. Left 2 units and down 3. Okay. We can also do the transformations to this point. So reflection in the x-axis, we're now here. Horizontal compression by 1/3, so we're at -1/3. Left 2 units and down 3. Right here. Okay, because we've shifted down 3 units, the horizontal asymptote is now at y equals -3. And we can draw in the curve. Okay, so that's the graph of f of x with the equation above here. Okay, again, we can state domain and range. Okay, domain is still all real numbers, okay, or in interval notation from -infinity to +infinity. And the range, okay, because of the reflection And because we've shifted down 3 units, the y values that are possible now are the ones less than 3, less than -3. Okay? Or in set notation, y goes from -infinity, so bottom to top, -infinity to -3, not including the value of -3 because of the asymptote. All right, here's the fourth example. So for this one, our base is 1/2, and so our parent function is going to be 1/2 to the x. Okay. Now our transformations that are going to be applied, the a value is 1. In the exponent here, those are the transformations happening to x values, so those are the horizontal transformations. Again, we want to make sure that that exponent part is common factored, just like when we did transformations before with all the other types of functions. So here we get 2 times x plus 1 in brackets. Okay. So the 2 is going to indicate a horizontal compression by a factor of 1/2. The 1 indicates a shift to the left 1 unit. And finally, the -2 that comes after here indicates a shift down 2 units. Okay. So let's start by graphing the parent function. The y-intercept is at 0, 1. Okay. There's our parent function. Now we're going to take the key points and apply these 3 transformations. So again, let's start with the y-intercept point. So horizontal compression by a factor of 1/2 doesn't affect that point. We are going to move it to the left 1 and down 2. So that point is now here. Okay. This point here, horizontal compression by a factor of 1/2 means the x value is now 1/2. And then left 1 unit and down 2 here. Okay. At this point, horizontal compression by 1/2 means we're at an x value of -1/2, and then to the left 1 and down 2. Okay. This point, horizontal compression means the x value is now -1, left 1 unit and down 2. Now here. Okay, horizontal compression by a factor of 1/2, so we're at -1.5, and then left 1 and down 2. And then finally, this point, horizontal compression by 1/2 means we're at an x value of -2, and then left 1 and down 2. Okay, because we've shifted down 2 units, the horizontal asymptote is now at y equals -2. Okay, and then we can draw in our exponential curve. Okay, so that's the graph of f of x. Okay, let's state domain and range. The domain of this function is all real numbers. Okay, or in set notation, -infinity to +infinity. The range, because we've moved down 2 units, is going to be all real numbers for y, such that y is greater than -2. And in set notation, we can say that as y values go from -2 to +infinity, not including -2.